Right. So in the previous class, we started with convolution. We technically started with definition of convolution, how convolution you can, as an operation, you can use convolution. And we talked about that you can basically use convolution over a two distribution, how you can basically combine two distributions together using convolution, how you can basically combine two polynomial basically function and using convolution. And we also went basically over the one-dimensional convolution, basically it's like a example of just if you basically have one vector as an input. We saw all the differences between kernels, how you can basically flip a kernel, or basically what are the definition of kernel. And we talked about that in reality, what we do is not convolution, is actually autocorrelation, because the only difference between convolution and autocorrelation is that we don't flip the kernel, right? And so in reality, the libraries that we use, they don't flip the kernel. They actually use that. And it turns out to be the same thing. You learn the same thing technically. Now, what we want to today go over is the multi-dimensional convolution. And now the idea here is that you, for example, have an image. And image by start, you have like a 3D image, like a 3 channels, red, green, blue, RGB. And your goal is that I want to learn something about this image. Okay, so I want to basically learn contextual, features from this image. And again, one of the main features of convolution is that feature extraction. It's really good for feature extraction. Now, overall, the way that the idea of a convolution is that convolutional network is that you basically pick an image and you try to go through the layers of this network. You keep processing this image with the goal to increase the depth, increase the overall depth of the image and decrease the spatial dimension. So if in this example here that you see this image has 3 depth, 3 channels, and this is kind of like a larger. As it goes through the network, it becomes smaller and smaller, but the depth increases. Okay. The reason the depth increases that basically the depth of this is called an activation map. It's all activation. The depth of an activation map comes based on the number of convolutional filter applied in the previous layer. So if in this layer, like this activation map goes to a layer, and in that layer, like let's say we add 100 convolutional filter, this depth is going to be 100. Okay, so what happens here is that a convolution layer gets, let's say, it's an activation map. So that goes here. Let's say this activation map right now, it's like has depth of D. Currently has depth of D. That means it has D channel, D activation maps, right? So when you want to process this, remember, bring marker myself. So if I want to process this activation map in a next convolutional layer, I need to be sure that I apply basically certain number of convolution. Normally you increase the depth. So let's say this was D, and now I want to go from D to P, where P is much larger than D. Okay, the number of depth, basically the depth of the image. So in order to do that, when you apply convolution in this layer, you apply basically P filters. Okay. Now, one thing that's important to remember is that when you apply P filters, each filter of yours need to scan basically every dimension of that image. Right? So every filter now has enough like a higher dimension, because you need to basically scan the whole box, whole basic activation map. And then you basically do some sort of like a summation or average over the result of those filters into one activation map. That means if I apply one filter, that filter should be same dimension of this activation map. So if I have P of those, I end up with P output. Okay, each output has depth of D, but we don't want depth of D for each filter. What we do, we basically sum those together, like kind of like imagine you have 10 images on top of each other, you press them into one. that one becomes the output of one filter. So if you have P filters, you end up basically with like assuming that we kept the dimension the same, but this becomes P. And so on. As you go through, you keep adding filter. The more filter you add, the higher the depth goes. But why do we apply filters like that? Why we keep trying to add more filters? Because the idea here is that these filters are responsible for learning features about your data. So basically, these filters, they start scanning the image, so more like a local dependencies on the image, because these are like a local areas that the filter basically, a filter starts from here and then moves, right? So basically, you do local, basically, scanning, and each filter is going to learn something new. And through the process of learning, what will happen here is that through the backpropagation, you update those weights and parameters of the filters, towards what you think, what your model thinks is more important to learn. So that's the whole idea. Each filter is exactly as what we saw. It's like a matrix of weights, for example, and you apply a filter, you get some output, you pass that output, it keeps going. At the end, you pick that output, you're flattening the output, because this, you cannot use it in a fully connected layer. Fully connected network need to have a dense input, right? One vector. So what you do, you pick this and you're just simply flattening it. Now you have a really long, basically, vector. You connect that long vector to maybe one or multiple fully connected layer, and you make your final prediction. Now, when you make your final prediction, it's here like you have some cost function also. You compare the cost function and you say, oh, now I have this much error, so you backpropagate. When we backpropagate, the first couple of layers are straightforward. It's like a fully connected neural network. You just do backpropagate through the network and update. At the end, you update the weights, right? But as soon as you go to here, the dimension doesn't match, right? Because now you have a vector of gradients, but your data is in multi-dimension, right? So what you need to do, you need to basically reverse that flattening process. Like the easiest scenario is that by you memorizing like where this position here, where it was in this multi-dimensional, and you basically basically convert the vector or a dense vector of gradients into a multi-dimensional, basically, matrix of gradients. And then that basically you pass that gradient backward, right? So that's the whole idea. So it's like we will just go over the basically the calculation and learning, but that's the forward and backward process. Okay, so. Now, we also saw that in the previous class that the convolution operation basically was kind of like that. So if you're trying to, you have this input and you have a kernel and you are trying to do a convolution and find the location ij. So ij here is the index that you are trying to calculate for. That means you have this, and let's say this pixel here, this, for example, is location ij. And you are trying to do convolution, a filter over this, and see what will happen to the value of this inj after the convolution. Okay, and that's basically how you get the value. So here, this summation is you sum over the region that covers that matrix. What does that mean? That means in a simple 2D example. So if this is my image and this is my convolution. So let's say this. And I'm interested basically to find the value of this after convolving this filter on this image. So the first thing is that you just pick this filter and put it here. This becomes that region, right? So M and N becomes from here. Those points are the M and N. Okay. So when you want to do convolution, basically it's like let's say this is 0, 1, 2. So it's going to be 1. This is 1 and 0. This is 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 2. So this becomes from 1 and to 2, and this one basically goes from 2 to or 2 to 3. 2 to 3. Right. So this, if you put this on that convolution, it says the input mn. So input mn, so m comes from 1, sorry, m and m. So this goes from 1 to 2. This goes from, 2 to 0, 1, 2, 3, 2 to 3, yeah. So this becomes input 1, 2, first one, times basically kernel. And then you see in the kernel we have I minus m. So what is I is 1. We're calculating, we're calculating for this point, yeah, I. So this is 0.1 and 2. That's the point we're calculating. So I is 1 and basically j is 2, right? So I is 1 minus and j is 2 minus. So, and from here, sorry, I said reverse. I said this reverse. So this is 0, 0. No, this is for the filter. So let's put this away. So this become 0, 0, 0, 1, 1, 0, 1, 1. Okay. So we basically pick this filter, and if you do 0 minus, what's the number that we have? 1 and 2, 1, and 0 minus, what's the number? 2. So this basically becomes kernels minus 1, minus 2. Minus 1 is basically reverse in indices on the array, right? So basically, if you put that here, so this becomes technically multiplication of whatever is this value times this value. If you reverse it, basically, you know. And then if you go to one more, this basically goes this value, right? And so on. So every time you do minus, that this becomes on your matrix becomes negative indices. And if you think about a vector, if this is 0, 1, 2, this is indices 0, 1, 2. If you say indices minus 1, basically, is this one, minus 2 is this one, minus 3 is this one, right? If you go basically minus 4, is this one, right? So that's how the negative basically will work. So every time this basically gets something negative, which flips the values, so you count it the other way around, and basically you multiply this by whatever input index location you are on the matrix, and you sum. Why we are summing? Because the output of putting this on this should be one value, like should produce just one square, right? So it becomes multiplication of individual plus like a summation, and it gives you one value. Now, if you had another channel here or another channel here, this vector also would have 3 channels. So you would have get 3 of this, and you sum all those 3 or average or weighted sum into one square, right? So that becomes doing the convolution here. But that's basically what this function tells you, right? If you can input, you find the range that you're basically going over for a certain, for a given index point that you're calculating. You're basically finding the index value, flipping the kernel by doing a minus that whatever is mn at that point, and it gives you the kernel value multiplied by the input value, and then basically you do summation. Okay, is it? Yeah.
RGB values are not maintained separately.
RGB values, they're not maintained separately.
You add them up, you said, right?
Yes. Yeah. So that's the whole idea. When we do basically kernel convolution over the image, if you have 3 channels, you get 3 output, but you need 1 activation map per kernel. And as you go through this, or actually we have a good visualization for that. As you go through this actually become larger and larger, but you still need to combine those. So I think, yeah, actually, it worked. This is a great example. That's the 3 channels that you have. So you have these 3 channels. You basically apply kernel. You see, it gives you, each kernel gives you 1 activation output map. And then you combine those activation map into one basically matrix. That's how you do the convolution. So if you have, I don't know, if you have like here in this example, we have 10. That means you apply 10 kernels, 10 filters basically. Each filter had 3 channels because each filter need to cover every dimension of the data, right? So if as you go through the channels, so if we go to the next one actually in this image is also 10, but the next time from the next layer, if you apply a kernel, that kernel need to cover every 10, this image will have 10 channels itself when you apply a kernel basically. So you need to cover all 10, you know, as you see there are 10 here, and then you combine those 10 into one. I don't know if the image does show that. If it goes, did it go to the next one or no? So we're going to go on this playground. Yeah.
So just for the sake of simplicity, can we just flip the kernel? Just like flip it and then do the multiplication summation, like a cross correlation, but just flipping it? Because tracking these negative indices, it's a little bit confusing.
So kernel flipping does that, right? That's kernel flipping, convolution.
Yeah, because we want to do convolution, we flip the kernel.
So yes, but in reality, PyTorch TensorFlow, they don't do that. They don't have this. We're going to go back to this playground later, but let's go.
But it's going to give us the same result, right? If you...
It doesn't give you the same, like a result. That's not a correct way of saying it. It basically, you'll end up learning the same thing. That's the.
Before you switch it out, Professor,
Yeah.
In that, like after applying results on the 3 layers, just a second. Yeah, right now. So we have 3 maps, right? So
Yeah,
we just add it up. That's it.
So here so it depends. You can actually, so this 3 output, you want to combine it into 1. You can actually do a weighted sum plus a bias, or you can just do a summation, right? It's it depends on how but it's possible that mainly you see the weighted sum. You learn some parameters, or you can just simply do a summation. We will go back to this. This is like an image of it. We will go back to this playground. But now let's go. So yeah, this part in the like libraries that are out there, we actually don't do the convolution. We do cross correlation, which it's the summation, right? So summation still does the same thing. You basically go in a positive direction, right? So okay, so now the first thing we're going to talk about a convolutional layer. Again, the convolutional layer is basically a convolutional layer that does the convolution process for you. And convolutional layer basically contains kernel functions, and kernel function has the parameters, and normally you have also some bias function. You know, you add some bias function. You can already pre-compute the output dimension from a convolutional layer. So that means if you have a basically image, and you want to apply convolution on it, considering that you know the parameters that like the hyperparameters that you are selecting, you know already what the output is going to look like. Like this activation map, you can pre-compute the dimension of this. And that's pretty straightforward. So if you have an image which is W times H times D, like a height, width, height, and depth, and you're going to apply K kernels to it, or K filters in one layer. First thing is that, again, each kernel that basically you have is going to be applied basically over the D dimension, right? So that's important, and you'd sum those technically. But overall, if you apply K kernel, the output that you get, the depth of the output is going to be K. That's the first thing. So the depth out of every convolution layer is exactly equal to how many kernels you use in that previous layer, basically, or in that layer, technically. Now, the width and the height, you can compute it this way: width of the input minus f. Here again, you see here the assumption is that the kernel is a square, but doesn't need to be a square, right? Width minus basically width of the kernel plus 2p, and what's p here is padding, right? How much pad you added around the image, like a zeros and stuff like that, divided by the stride, how fast you're basically striding, moving this kernel over the image, at the end plus 1. And the same thing goes for the height. So this way you can calculate the width and the height of the output, and the depth of the output, basically activation map, you also know that is equal to the kernel. Now, how many parameters we are going to learn here? If you have basically every filter has F by F as F by F matrix, how many of those you are learning? Basically, you are learning K of those. But every filter also is important to remember will be applied to each like a dimension across that D, right? Remember the image that we saw? We applied 3 kernels to image and summed the values. So 3 kernels means why did we apply 3 kernels? Because the image was RGB. So here, because your image has D dimension, every kernel that you apply should have D dimension, right? So that F times D, that's the number of parameters in one kernel. And if you have K kernels, that's the total number of learnable parameters that you're going to learn, plus the bias, if there is a bias term basically you are using. Does that make sense? Yes. All right. So again, just think about it like a, the easiest way for you to remember is that the depth, if you're creating a kernel, the size of that kernel matrix, it's your decision, like from the height and width perspective, but the depth of the kernel should be equal to the depth of previous layer's depth, and the output of this current layer as the depth of the current layer will be equal to exactly how many kernels you apply. So those are kind of like a fixed, is always equal, but the height and width basically will be calculated using this formula. Now, in this just as a reminder that what we do is cross correlation and technically not convolution basically. Okay. So now this is another example of convolution, as you can see. So you have here we have basically input has one depth, like one channel. So your kernel also need to have one channel, and if you basically put this kernel here, it gives you this value. If you put this kernel here, for example, it basically gives you this value. Here, there's a padding, right? And so on. So that's the whole process of convolution. You basically slide this filter, do a weighted sum, and you calculate the values.
So this gives us the first activation map, right?
This becomes, so because you apply one kernel, one dimension, one activation map.
So what's the next step up?
So depending on how many kernels first you apply. You normally don't apply one kernel only. Because your goal is in convolution to increase the depth. Right? So in each layer, you technically try to add more and more kernels apply, number of filters.
I think last time you suggested some kernels for specific use cases.
Yes.
But how does one go about picking kernels?
So, you can select manually enforce kernels. That means that when you create a convolutional layer, so there's a parameters normally those libraries have that kernel initialization, you could enforce your kernel weights yourself. But in practice, we don't do that actually. The models learn that, because as the whole idea of this, this local learning, that what the convolution does is that to learn features for some downstream task. So if you are trying to do image segmentation, right, and your model at first doesn't know what kernels to learn, as this goes down, you have some prediction output, and you compare it with the segment, you're like, oh, this is not a good segment. So the model, when you do backpropagation over time, the model understands that in order to do segmentation, maybe I need to learn edges. Maybe I need to learn basically separation. So it updates certain weights for certain kernels to adjust for that task. So that those learning happens through the backward propagation. And we don't enforce those basically, because imagine if you have lots of kernels, like a long model, you're not going to manually enforce those kernels. You basically try to learn those, right? So, now, the next thing about convolution was, as we saw that the goal was to add kernel, increase the depth, but also to reduce the spatial dimension, like decrease the width and height as you go forward. Why? Because if you keep your image always the same and you keep learning lots of depth, it becomes so many parameters, right? It becomes really computationally expensive. So with adding depth, but also in order to make it more, computationally cheaper, basically, we start reducing the dimensions, right? So some strategies. One of them is like, for example, we're going to talk about downsampling, and downsampling basically the idea is that I don't need all the pixels, all the adjacent pixels, right? Because there are some of those that carry similar information. So instead of having, maybe I could basically select some of those based on some approaches. So one technique is called subsampling. This is subsampling. you technically pick every other pixel. Right, so you start from the first like a corner and like a some like a raster scan. You pick every other basically pixel. Here basically it's kind of like max. This is called max pooling. So assuming that you have a kernel of like a 2 by 2, you pick the maximum value and you project the maximum value. So you drop the other ones. Your assumption is that 6 here has enough information that I don't need the other ones, right? And then here, for example, you do average pooling. So you average the values into 1 and so on, right? So yes, I probably have this question that aren't we using some information? Yes, but just through time, basically, we will see that not all those pixels are necessary for doing certain tasks. And especially if you think about from the perspective of image, the colors degrading until you change the next color, maybe you don't need that smaller values. You can just have a sharper change as you go between 2 colors. So you can basically do like a pooling as a way of to do downsampling. And in pooling layer, so the way that we do pooling is that if you pick an image, and this is not an image, let's say the activation map. Okay, this is an activation, 1 layers of the activation map that you have. And you're going to pass this through a pooling layer because you're interested in to reduce the spatial dimension. And in the pooling layer, also we define a kernel. But the kernel in the pooling layer doesn't have any weight, nothing. It's just a shape, empty shape. You're not learning anything. 0 parameters will be learned in these layers. The only difference here is that we will call this, for example, a max pooling. And you pick this and put it here on this 4. And you pick the maximum value out of those. That's it. There's no parameter, no multiplication, nothing. It's just simply just a matrix in order for us to make it easier to slide. And you also have the same parameters, a stride, padding, and everything. You basically can use the same thing, basically. Okay. So pooling layer is just depending on also the types of pooling. You do max pooling, average pooling, so they are different. You're not learning anything, basically. You don't basically learn any parameters. No parameters learned. But also, remember that the purpose of pooling, it says that we know that image, remember we said our image are basically in convolution, we said that is, equivariance, right? That means that, it's basically, also if you do some transformation, it doesn't change the convolution process. So we are technically, if we remove or some pixels, that's not going to change anything. It's going to be invariant. It's not going to impact the output. If we drop some of these pixels, it's going to be the same thing, because they're not necessary for the task that we want to do. And our goal is that to reduce the spatial dimension because it will reduce the parameters. And also it helps to avoid overfitting. Why it helps avoid overfitting? Because if you let a model to see every details, it might memorize it. But if you every time dropping some pixels, the model doesn't see a full picture of the image, right? So that helps with, not basically overfitting. Also, you're not learning too many parameters to overfit. That's kind of overall like a way of helping or basically preventing overfitting. Now, is that clear?
Is it just one time pooling before this the convolution, or we can do it at each layer like the drop off?
So actually, good question. We actually, it's kind of like as practice, you apply after maximum 2 or 3 convolutional layer, you apply poolings. It's like every convolutional models you see out there, you see after every 2 convolutional layer, there is a pooling. Sometimes you might see after 3 convolution, there's a pooling, but you always keep applying pooling because convolutional layer by default, the only way a convolutional layer will reduce the spatial dimension is if your stride is more than 1. You kind of like have these jumps in order to make the output smaller. Otherwise, if you do a padding and your stride, for example, is 1, you keep creating the same dimension output. You're just increasing the depth. So that won't be helpful for reducing the dimension. So then you apply the what's called the pooling. Why don't we try to just reduce the dimension on convolutional layer? Because we don't want to miss some of the pixels. We want the kernel to learn everything. So you let the kernel go, basically sees all the pixels, get some learn some feature for you, And then after you learn the feature, you go over the feature, you say that, okay, some of this that I don't need. I'm going to drop some of this to reduce the overall dimension.
So how does the backpropagation work in?
We're going to go there here. We're just going to go there soon. So, and this is the dimension of the output of the pooling layer. Basically, with same story with minus, and if you have a padding, you add the same thing, 2 plus 2p here. So same basically equation, and you are basically learning 0 parameter. Depth doesn't change basically, you know, it's just depth 1 and depth 2 are the same because you're not doing any learning. You're just either doing averaging or dropping or something. You know, you just reduce the spatial dimension. You are not changing the depth of the activation map. So now, so let's just talk about it, like here, max pooling as an example. There's something called weak prior. So weak prior, if you think about the Gaussian distribution with a large standard deviation, right? So if we are looking at this Gaussian that I have a really large standard deviation, we call this as a weak prior because it has a high entropy. Right? Lots of randomness. Every time you sample could come from anywhere. Right? It's really wide. If you have, for example, Gaussian with a really small prior, a small standard deviation, the entropy is low, you know, that basically becomes a strong prior. When we talk about something like max pooling, which you go over this image at these 4 pixels and you pick the maximum out of those 4, you drop the other one, that's called infinite strong prior because you give 0 probability of retention for the other ones, right? You out of some nodes, you say that I'm going to drop all, keep only 1. So those that you are dropping get 0 probability of retention. The other one gets high, like a 100% probability of retention. That becomes infinite strong, basically prior. Okay. So now the next thing is upsampling, which is the reverse of downsampling, right? So what if we want to basically go back? Right? What if we want to go back to the same dimension that we have? Now, if you have a 4x4 like that, and you're like, oh, I needed to convert it to this. There are a couple of ways that you could do. You could just like an identical mapping, like exact same thing for every 4x4, 2x2, 2, 2, 4, and 8. You can do nearest neighbors, basically. You can do something like this, which one is this one? I'm not sure which one is this one. Now the way that it's ordered, I'm not sure what it's called, but and then you have something like this. Basically, it is to do interpolation, basically. Right? So there are different ways that you can go upsample. Basically, go back from downsampling to upsampling now. And overall, basically, this is going to be a good example that you can see that for convolution. You start with an image, and you see this image has this colorful like a 3D. As you go, you see the depth is increasing, the size is decreasing, right? And basically, you see you do convolution, max pooling, convolution, max pooling, convolution, the max pooling, and fully connect. So you do a series of convolution to learn features, and then you do reduce the dimension, and then you continue until you get to enough depth that you need for your model, and you do fully connected. Basically, you flatten. This one, you need to convert it to a one long vector, and you do multiple fully connected and some classification. Okay, so that's the overall architect. That's what basically we do. There's no image here. All right, and the final layer in your model, in your convolutional model, it depends on the downstream task. You do if you do a classification. Your final layer need to have a softmax or sigmoid, depending on like types of classification. If you do regression, basically you do a prediction as like a real number, and it could be some other task specific, depending on again what you're doing. But now let's do one thing here. So let's go to this one first. So this is the output of the last layer, and as you can see here, we have this flattened layer. That means this basically we got, and we flatten those, right? It becomes a long vector, and that goes to the last node, which we're making a classification. So you have this type of classification that you do. For every one of those, basically, you do classification is a softmax. You get one probability, and among this, you select one of those that has the highest probability. Right. So the output is, just imagine, is a fully connected network from here to here, technically. Okay. So now let's look at this end to end. So this is it. This doesn't come up. So here, let's just start here. So you see we have 3 channels, red, green, blue. And here, the first layer, convolution layer 1, we are applying basically 10 kernels. So, okay, that's why the depth is going to be 10. So when you apply 10 kernels here, every kernel by itself need to operate over 3 channels. Okay, so every kernel, every 10, basically we have applied 10 kernels. Every kernel need to scan all 10 dimensions and combine them into one. So this, what you see here, 1, 2, 3, 4, 5, through 10, those are the output of 10 kernels averaged over 3 channels. We're going to just look at that. So if I pick one of those activation maps, so this one, for example, which is the output of one kernel, you see it gets the output from 3 channels. It creates 3 internal activation map, and it combines those 3 internal activation map with a bias into one activation map. Okay. So because we are saying that we apply 10 of those, basically, so because we apply 10 kernels, so you get 10 outputs, right? Then we go to the next layer. In the next layer also, we are applying 10 kernels. However, every kernel is going to go over the 10 from 10 output of the previous layer. So if we pick one of these, oh, sorry, what did we have? This is a ReLU, actually. This is not a, sorry, this is not the convolution layer. That's just some nonlinearity. So this one, yeah. So you see this one, this is basically, that's the output of one kernel from the second convolution. That one kernel has convolved over 10 dimensions. That means this one kernel has itself is a matrix of 10D. It's like a, not 10D. It's basically a matrix that has 10 channels, right? So we put these 10 channels, over, each channel over an activation map, do a convolution, you get the outputs, you combine those outputs with a bias into one activation map, right? And you keep repeating this. So as you go, you can see why it computationally become expensive, because the more depth that you have, each kernel need to have same number of basically dimension for weights and parameters, right? So if you don't reduce the spatial dimension, then it's going to be really expensive, difficult to process. So now, so this one, and this as we go, so this is like a smaller and smaller. So let's see max pooling. Oh, actually, we can do max pooling. So this is an example of max pooling. So it goes over the, not a good clear example. Let's see. This one is better. So it goes over those pixels, and it basically, for every 4 pixel, it returns one pixel. So from 26 by 26 goes to 13 by 13. As you can see, it still kind of look alike. You know, it just becomes sharper from the perspective that if you look at the image, because it drops, you know, all the smaller pixels and keep the larger pixel, like the larger value. So, and that's the idea. Like, you know, we are not losing much information here. All right. That's it. Any question on this? Does it answer all the doubts? Yeah. Yeah.
So we're still having 10 channels in each layer.
In this example, they haven't increased the depth. Let's see if this. Let's see if have. So this is kind of like a playground. I don't think it does allow you to. Oh, let's see. You need. No. Yeah, it doesn't allow you to change the size. But otherwise, if you There's a pen here. Let me see if it does. Yeah. So yeah, it does. But in here they have kept the kernel 10, 10, 10, 10. Otherwise, you couldn't visualize it. It's kind of like how
Kind of, right?
Yeah.
So these outputs of like all those kernels, so it is after that neural network was fully trained.
This is after the neural network was fully trained. At first, so as you train your neural network, you could have, like from the perspective of learning, you could actually maybe start having some internal function that you can do some visualization. That it shows you that what you are learning as you go. So you can basically do something like that. Actually, we have a lab on, I think we have a lab for beat or like a vision transformer and image captioning. I did record it over the weekend. In that, we do something like that. We are adding an internal function that as the model learns, it also plots the attention matrix to show you that what is at that moment, which part of the image at that moment the model is focusing on in order to predict that certain word. So you can basically visualize like that, but this one is already trained model. If your model is not trained, this is going to be totally random at first.
So here is it like in the first layer they use 10 kernels and the rest of the layers they just use one kernel.
They keep using 10. As you see, 10 is fixed. If at this layer, at this convolution, I pick one filter, the next convolution doesn't get 10 input, it gets 1. The output, the depth, technically this activation map that you see, you can look at it as depth, right? If you stack this on top of each other, it becomes this, right? But this is technically a slice, like there are 10 of this, right? So if you use one kernel in a certain layer, you're only going to get one activation map. So the depth from 10 goes all the way to 1, which you lose the meaning, because the goal is to increase the depth to learn more features. And as you can see, this actually, let's see if you can zoom in here. Maybe if we pick something. Maybe, yeah. So as you can see here, every kernel output, the activation map, it's technically learning something different. Like you can see those kernels are like one kernel is totally maybe focused on like, I don't know, it's like, like a color maybe. This one is focused on lighting, it's like where is the brightness. One color maybe focused on darkness. Color here, this one, like one activation map, maybe it's focusing on the edges or maybe shapes. And as you go through every kernel, depending on what you are trying to do as downstream task, we'll learn something related on that image. And we will see that later, that as part of like a transfer learning, or like this whole idea of fine tuning and stuff like that, is that if someone has built a large model like this, trained over the image and stuff like that, what basically we say is that this early representation, these early learnings should be the same across different images. Edges are the edges, colors are the same. So you don't need to relearn this. That's why like those type of techniques work, because someone else has trained it, it has already learned. All you need to do is that maybe pick the last layers, those flattened layers, and just retrain only those layers with respect to your task, right? Because you don't need to relearn basically some of these features. All right. Okay, so that was the convolution over there. Now let's go to the backpropagation. Okay, now how the learning basically happens. We start with the last layer, which is the fully connected. And fully connected is, I don't need to go over it, it's just a fully connected neural network, right? So you have a cost function, and you simply calculate the cost gradient of cost with respect to input of every node. And that's basically what you need, right? That's how you backpropagate back. If you have this now, this is the out gradient with respect to the fully connected. Now let's say you have with respect to all the fully connected, and you want to go to flatten layer. The layer where we flatten, like we have this like activation, and we convert it to a vector. So here, all we need to do is that to pick that gradient vector and convert it to the same shape that we had pre-flattening, right? We just need to figure out what's the index location for every gradient in that activation map. So that's the fully connected flattened layer. You don't have additional gradient. Same gradient value, you just reshape it basically. Okay, so it's like a reverse basically. Now, let's go over the pooling layers. So what happens for gradient and pooling layers? Let's just start with max pooling. So if you think about when here you have this 1, 2, and you did a max pooling among this, and you picked one of those. So let's say this one was the maximum value. You drop the other 3. So if you think about from the perspective of forward, backward, these 3 did not participate in the anything calculation that you had in the future, right? So the gradient should be 0. So this 3 basically will get a gradient of 0, and this one, because also in pooling layer, remember we don't learn any parameter. There was no parameter. So the gradient for this one is exactly the gradient of the input to the previous layer, basically. So gradient of loss with respect to pool output, right? The output of pool layer is input to the next layer, right? So the same gradient that you have, you just use it for pooling layer because you don't learn any parameters, right? And for the one that they were not part of the max pooling, that you just give them gradient of 0. Now, on the other end, if you are doing like an average pooling, like average pooling means that you had these 4 pixels and you average them all into 1, right? So you want to basically go backwards. So you're like, I have the gradient up to this point. All you need to do is that this gradient is from average of these 4. You basically need to divide that gradient among those 4. Same idea, right? So you pick the gradient and divide it by pool size. What was the number of pixels that you went over as for averaging? So that becomes the gradient of individual. Is that clear? So max pooling is straightforward. Average pooling, all you need to do is that just average the gradients. Yes.
During the pooling, there were no parameters,
Nothing.
but before that, we are not training the parameters, right? We are not updating the parameters when we are doing pooling, basically.
So when you do pooling, there is no parameters in that layer. The reason we are doing this back propagation through pooling is if you think about what's happening in the pooling layer, you have an image and you reduce the dimension. So when you want to go back, you have the gradients that you have doesn't match the data that you have, the activation map that you have. So in order for your gradient to match the activation, that's why we reconstruct the pooling layer, even if we put 0, just to be sure that this gradient will match the dimension of the input to the pooling layer. So we can traverse backward. That's the only reason we go through it. So we're going to have an example right now. So think about this one. So you have an input matrix, I, and we are doing a max pooling with a stride do, and then this is basically what we have, the output after max pooling. Now, let's assume the gradient of the loss is this, which was basically up to the output of this max pooling. So you have 4 values, your gradient of the loss is 4. Now you want to traverse back, you basically want to reshape this gradient for before the pooling. All you need to do is that, so remember where this 5 stands on the original data is here. So put the gradient for 5 here and 0, 0 for that one, right? Then you go for 6, put the gradient for 6, 0.2 here and 0, 0, and so on. So basically you reshape your gradient to matches the shape of the input, exactly. If you are doing max pooling with a stride of 2. Now, there is a scenario, what if there are overlapping data points or overlapping pixels, right? And overlapping pixel means this. If you're, now if we have this to be a 3 by 3 and you stride of 1, the first time you put this on this becomes here, right? Then your stride 1 becomes here, okay? Among this and this, 9 is max all the time, right? And sorry, what's we are doing 2 by 2 still. Sorry, we're doing 2 by 2. This is not the we're still doing it's supposed to be a 2 by 2 stride of 1. So this becomes 5. Then you shift it by 1, still 5. then you shift by 1, 4, then you go 1 down here, it becomes 8, then here all becomes 9, and here 8, right? So you see, now if you think about from perspective of the reshaping of the gradient, we get this, right? But this gradient, 0.1, right? This comes from this corner, correct? So there is this one here, right? But if you think about 5 also gets another gradient. It contributed to 2 basically outputs, technically. So the gradient that comes back to 5, when you want to reconstruct, it should be summation of these 2. So it becomes 0.3. When you go to 4 is the same thing, basically remains the same thing, 0.3. But let me send this down. But when we go to 8 and 9, you hide this.
Hide floating.
Floating.
Next one.
Perfect. So if you think for 8 and 9, 8 participated twice. So this and this, 0.7 plus 0.4. And 9, it should be summation of these 4 values. It's still max pooling, but you have overlapping, basically, pixels. Okay? Is that clear?
So in forward propagation, are we saving the indexes of?
So not necessarily. There are ways that when you go back, you can basically try to mimic the process. We're going to see a couple of those as we go through the slides. Just bear with me a couple of slides. We will see that. Yeah.
The gradient of 9 it adds up to 2.8.
What's this one? Yeah, so then that's a typo. It should be a summation, right? It would be, yeah. Thank you. So send me a reminder later to fix that. Okay, let's see. 9. Yeah. So, so that was for the pooling layer, but then you also have activation, and I'm not just going to go over this, but we know for activation, like depending on what activation function you use, you have some gradient. Because remember, you could have convolution and activation on top of that. Right? So, and depending on what activation you applied, if, for example, sigmoid, we know the gradient becomes sigmoid times 1 minus sigmoid. Right? So basically, you do back propagate through a sigmoid. One thing also remember again, for activations, you have this linear region, you have nonlinear regions. Nonlinear regions, you normally have larger weights. Okay, here and here you normally have larger weight. Linear region weights are more proportionate. The problem with nonlinear regions is that as you back propagate, they have basically it tends to end up with like a gradient vanishing and stuff like that. So if your weights are here, you have a higher chance of gradient vanishing. That means the gradient goes towards 0. You're like does that basically if you end up with gradient vanishing, you're not doing any learning, right? So that's why we try to not have weights to be always here, try to be more toward linear, because it's also easier for learning. And also it's kind of like if you're on the 2 tails, a small perturbation in the data has really large outcome, like a large fluctuation in the outcome. But if in a linear region, if I change data by a certain amount, it's going to be linearly increasing. I kind of have some idea of like it's proportionate, the amount of change. If I change the input from 2 to 2.5, you know, I'm going to get proportionate output change. But if you're here, you don't know, like it might fluctuate either really high or, you know, really low. You know, it's kind of like that's the problem. So, and then we want to calculate the gradient with respect to convolutional layer. Okay, so so let's say you have this layer and you're basically doing a convolution, and we already have the gradient up to the activation map, the output of the convolutional layer. Okay. Now you want to do backwards, so that means you already have maybe, let's say, this gradient right? Let's say these are the gradient for this corner, and you want to backward, and this is your filter basically, right? So if you think about from perspective of the gradient, let's say this is your activation map. Actually, this is its activation. Each pixel here, or pixel in the activation map, or each value, it was basically a weighted sum plus a bias, right? Remember, when you put the filter, you do a weighted sum plus a bias, and you might have applied some nonlinearity. But let's assume just linear, weighted sum. So if you have the gradient up to this point, up to that point, that's the gradient of the output to the output of activation map, and your goal is that to calculate the gradient with respect to the input that generated this, also with respect to the weight of the kernel that generated that. So there are two gradients we need to find. Gradient with respect to the input, gradient with respect to the weights, basically. So for the, with respect to the input, it should be a straightforward. Why? Because if I want to find gradient with respect to xi, so let's say this is W11 x1213 plus W12 x1214. It's just 12 is a row, 14 as a column, plus W, sorry, I'm going up, 21 x 13 plus W22 x, let's say 13, 14, plus a bias, right? So if I'm trying to calculate the gradient with respect to x1214, and I have the gradient up to the output, as a chain rule becomes the gradient up to this point times gradient of this point, which is the output, with respect to this point, right? This data point. So this is that output. This is this. Gradient of this with respect to x1214 is the W, right? Just the W. So that's why you just simply multiply the gradient up to that point that you have by, so this is with respect to the input becomes the W, the filter weight for that corner, right? So it's just straightforward. The other way around also, if you do with respect to the filter, that means you're taking, let's say, the gradient with respect to this is the X, right? However, we need to also remember the overlapping concept. Filter is not just participating in one corner. You have to slide it. It's going to be summation of those gradients. So that's why you also have this summation across any point or any indices that filter weight has basically contributed toward. Even for the input, if you think about this point, x1214, wasn't only part of one stride. As you stride, you might have been actually part of 1, 2, 3. Also from down, you might have been part of that. Because you remember, if I am here, so, and this is my kernel 2 by 2. So first, this is not part of the kernel. Next time I shift here. So now this point is part of it. Also next time is still part of it. Now, if I go all the way down, is part of it? It's part of it. So that data point, that pixel was part of 4 basically operations. So you end up with 4 gradients for that data point. So that's why you have this summation. Depending on how often you have seen as part of one activation map, that specific kernel or that specific input. We're going to see it as in a matrix, you know, I don't want you to imagine it in your head, but let's look at this. So you have this activation map. So you have this input over activation map, and you have this filter, and we're basically going to stride this over here, and we are doing a stride of 2. So you put 1 time here, you jump, and you go here. Actually, a stride of 1. So wait, a stride of 2, and then you go here again, and then you go here. So you get 4 outputs, right? So now we want to see that if we have, let's assume that we do have, this is just same image of what we just saw. So actually, let's map it. So you see the output matrix Y00. So how that one being generated, it's basically coming from this operation. Weights of the kernel times that input to that in that square. So F00 is the weight of the kernel times the input and so on. Right? And that produced this value. Right? And for the next one. And as you can see here, we didn't flip the kernel technically. It's just cross correlation. Now, if we think about y00, it's that summation, right? Now, if you want to calculate the gradient of the loss with respect to x00, we're using a chain rule, gradient of loss with respect to this, which is the activation map. We had it through the backpropagation, times gradient of this with respect to x00, and becomes this one, okay? And if you have overlapping, we're going to see overlapping, then becomes summation. So overlapping means if we pick this example, so if you think about x02 was part of calculating y00, also part of calculating y01, right? But this x02 contributed to both of this. So if you want to calculate the gradient with respect to that, you need to look at both equations for y00 and y01, right? And then you basically become summation of two gradients, right? So it becomes summation of two. That becomes the gradient with respect to x02, basically. Right? Anytime you have overlapping, basically, pixels or data point, then you need to do a summation over the gradients. Now, let's look at with respect to weights or the kernels, because the kernel strides over, right? So it's going to, every weight in the kernel basically participate in multiple locations. So let's say we are interested in F00, first weight of the kernel, and we stride, so a stride of 2. So first time you are here, then you go here. So F00 is here, F00 is here, then you go down, F00 is here, and F00 is here. Right? So it's the same story. And you have the activation output and you have the gradient up to the activation output. So you want to basically back propagate toward the weight. So you want to calculate the gradient with respect to F00, which all you need to do is that you have this 4 output pixel. F00 is in each one of those. You calculate the gradient, becomes gradient of loss times x00 plus loss time gradient of loss with respect to this one times x02 and so on. So that becomes the gradient of loss with respect to one weight, like one weight value of a given kernel. Is that clear? Now, one of your friends asked, should we keep those, should we keep those, like, should we memorize this, like through the back propagation? How could we keep track of this? So actually, it turned out that you could, in the back propagation, use convolution process to do the operation. How? So let's say, let's look at this image that you see, and look at the four basically values that you have. Those 4 yellows, right? They have some similarities. If you think about them, they are falling in the first 4, correct? So they are basically falling in the first 4, like this. Is it like a 4x4 or 3x3? 3x3. So first. Right. So basically, they are here, 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 here. Okay. So one thing we could do here is that if we pick the basically this what's called this y00, y01, and those 4 basically we have. If we dilate them, add some basically dimension in between. This is the dilation. So if you have of the formula. correctly. I think dilation is S minus 1, if I'm not wrong. S is your stride, right? So basically, solution. Should be in your other booklet. Dilation here, yes, S minus 1. So S minus 1, S minus 1. You put basically 0, 0, 0, 0. Okay. So if you pick this and here this put those values that we have y 0, 0, we have y 0. L y 0, 0, gradient y 0, 1, gradient y 1, 0, gradient y 1, 1. Okay. So we had the gradients up to that point, right? Remember we said we had the gradient up to this point. And that's the gradient. And what we do, we dilate the gradient. How we dilate it, we look at what was the stride that we have. We add a dilation in between these rows and the columns. And that becomes the new matrix, okay? Now pick this matrix and put it on the original data that you have. Move it, right? So first time you put the matrix, that matrix exactly, this gradient, this gradient, so you have 4 corners gradient, right? If you put it on this image, the 4 corners being multiplied by this, by this, by this, by this, correct? So that exactly is the same value that you got as the summation. So you basically, if you dilate the gradient of the activation map, okay, based on that formula, you're just using S minus 1 dilated, and convolve it over the input, it gives you the same gradient for the weights that you want. So that is 3 by 3. You put that 3 by 3 here, and you shift it. Right? That becomes the gradient with respect to. So that's an easier way in the back propagation, that instead of trying to do something funky, you just reshape the activation map or the gradient, and you do another convolution basically. The same thing actually we could do for the input. Which one? Yeah, let's see. We have this here. You have this also in the booklet, but so it's going to be a little different for the with respect to the input. Okay, so your gradient was 2 by 2, right? The gradient is still 2 by 2 because we have a 2 by 2 activation map. So if you try to calculate the gradient with respect to input, the one that we just saw, it was with respect to weights, but with respect to input, we're going to do the same here, reshape this and do a convolution, right? But here in this part, we are going to dilate and pad the gradients. So dilate basically means the same thing. You're going to add this 0, 0s here. So this is your gradient with respect to y00, gradient with respect to y01, y10, gradient with respect to y11. But so this is still the same thing, S minus 1. But you're also going to pad, okay? And the pad also is going to be P, I think if I'm not wrong, R minus 1, basically, and S minus 1. So R and S in this case is the same. So what was the original kernel that we are using is 3 by 3, right? So the height and basically width of the kernel. So if kernel is 3 by 3, you basically do, let's say height minus 1 and width minus 1. So it becomes 2, 2. So you add 2 padding up two padding on the right, and dilation in center. So you end up with this matrix, 0, 0, 0, 0, all the way. And you only have these four values, and in between also dilated 0. Okay? So now we have this. The difference here is that with respect to the input, you're actually going to flip the kernel. Okay? So now you pick the original kernel, which is this one, the filter matrix. Okay? Flip this. So when you flip it, technically, F22 goes here, F00 goes here, right? So flip was one horizontal, vertical, then horizontal, right? So this basically comes here. So this you end up with something like this. F00 is here, and F22 is here. Okay. Then you pick this and shift it over basically convolve it over this matrix. What will happen here is that any place that, if you go to this one, let's say for the X02, so when you convolve this over this, the multiplication that you are getting of these values by whatever matches on it becomes exactly this. F02 gets multiplied by this, F00 gets multiplied by this. So F0, 01, F02. So F02 gets multiplied by this. And what was the other one? F00 gets multiplied by this. That becomes the gradient of the convolution with respect to the input. So basically what we found out is that in the back propagation, with respect to the input and weight, you technically could do it using convolution. With respect to the weight, you need to dilate and pad and do the convolution. With respect to the weight, you only dilate and do the basically cross correlation. Those are the examples are in your basically booklet. The same examples for this matrix and applying the reverse convolution. Okay, so
I'm a bit confused. For weight and for input, like which one is both dilate and pad, and which one is just
Both.
dilate?
So let's do one thing. I think if I'm not wrong, we do have that slide, so maybe easier than me trying to draw it on the board. So if we go here. So if we are trying to calculate this with respect to the input, we dilate, okay, and then we pad, okay, and again, this R and S for padding. This is not for stride. This for the filters dimension. This one is for a stride, okay. So you dilate and pad your gradients. So now your gradient looks like this, okay. Then you pick the filter, flip the filter basically. You bring the filter and flip the filter, horizontal and vertical basically. That becomes your new filter. And you pick that filter and basically convolve it over the new dimension, new basically gradient basic activation map that you have. Basically you shift this over that. So if you are trying to calculate the gradient with respect to X00, when you put that here, the only place that you're basically touching is this, because remember you flipped it technically. So it becomes this times that. And if you go for X02, basically becomes this times that, because X02 was part of two locations as you shift it. So that becomes the same process for backpropagation using convolution again. Again, highly recommended, go through the slides, like try to look those. I cannot draw most of this on the board, especially with this board. But all right. So that's the convolution. And basically that's a gradient with respect to the convolution. There's something missing here. That was it. So that's a gradient. And the next thing is that like we just quickly talk about like the application of convolution, which you use it in image classification, for example. You can use it for feature extraction, object detection, for example. You can use it for transfer learning. Basically, you have this model that learns certain basically behavior, like certain image segmentation. You transfer that knowledge to another model. That model does basically get like a different type of task. You know, it's just that you transfer that knowledge. Because again, remember, if the features are learned, you can basically use those features. And this is going to be an example of the semantic segmentation convolutional model. As you can see, it just has some flavor of like a autoencoder. It basically reduces and then flattens and basically increases. But here we are using it for the segmentation. The idea here is that the flavor here basically is that like if you're able to break down an image and reconstruct it, right? It means you have learned the distribution, and then so you can basically use that for segmentation. Because if you learn the distribution, you learn the objects in the image, because you were able to break down an image and then reconstruct the image, right? So you learned about the image. If you learned about the image, you can do segmentation in it, or object detection in it. That's the idea here. We will have those later. So, and this becomes again for like a segmentation or object detection. The next thing here is like a pixel CNN. Now this is becomes first view of generative model. Okay, this pixel CNN is going to be first view of generative model in the class, which the perspective, because everything that so far that we have been talking about is just a deep learning works. So like a framework, they don't generate something for you, right? You just do classification or downstream task. But what if we want to generate an image, right? So this basically developed by Google, this pixel called Pixel CNN. And the idea of Pixel CNN was that it's types of autoregressive model, which we will learn today also. Which is autoregressive is anything that's sequential, basically you learn, like a GPT. You're giving a sequential word in order to complete a sentence. That's autoregressive. Autoregressive in image generation is that you generate one pixel at the time. So you generate a pixel, you use that pixel to generate the next pixel, and so on and so on. Right? So it's basically using the convolution. You're doing this image generation. There's one big caveat here is that if I'm doing a convolution here, I cannot see my next filter, next pixels, because I cannot see the future. I should not be seeing the future. So what you need to do here is that we do a masking, as you can see. In order to generate this pixel, you don't see this ones. You are masking future pixels. Any pixel that comes after you, you should not be able to see that. So you need to do some sort of masking on your filter weights. And then you basically, the idea will be that you learn, you keep as you go, basically you learn the pixels, so now you should be able to generate. So your filter basically becomes something like this. If you are predicting this pixel, you see this one's like you see as you go, it's like kind of like it becomes farther away, it's harder to see, but this becomes blind spot here, for example. You cannot see those ones. It's just a certain blind spot that you have, and you can do that by introducing mask. Basically, you have this mask value that you multiply by the output. So simply you do a convolution, but after you do a convolution, you multiply it by this and force some of those to go to zeros. It's like you didn't see those, basically, like come mask value. And this is like an example generated by a model like that, right? So if you have something like that, an autoregressive model like that, someone could, for example, randomly start with a pixel and then let the model to generate the full picture. Because the model needs one pixel at first, and then it continues basically building more pixels, right? So that's called Pixel CNN. Now, the thing about Pixel CNN was that it was like this study about adversarial basically attacks that if you introduce certain noise to the image, and then downstream task basically says that this was a dog, now it's an ostrich, for example, right? It's like a model easily can be fooled, basically. Now, in Defend for that, basically they came up with another paper was called Pixel Defend, right? And Pixel Defend basically, it starts with the Pixel CNN model. So you develop a Pixel CNN model because you know that this model as an autoregressive model, it learns the distribution, right? And we will talk about those soon. And if your model has learned the distribution of the image, because it can generate those, if it gets a new data point that is not like a real, is adversarial data point, basically the generation or let's say the likelihood is going to be really low, right? It's kind of look like an outlier. So basically you use that for outlier detection, because you see that, okay, if this is for adversarial image, you basically see that for certain type of adversarial attack, deep fool or DIM, and compared to the clean. So if this is the clean, the adversarial ones, is much easier to detect as a classification, because the distribution is going to look different than the original image that the model learned, the distribution that the model learned. So first one was pixel CNN, and this was this pixel pixel defend, basically. Is that clear? It's just, again, like you have the same convolution, you do one pixel at a time, and you just mask the filters every time. Even in back propagation, it should be same thing. You just account for the masking that you have done. All right. The next thing is comes residual neural networks, which is one of those really basically into like a great basically idea that basically came out, residual neural network, and is right now part of almost every models that you see, from convolutional model to recurrent model, basically GPT models, transformer models. They all have residual basically connections in those, or a skip connection, and basically introduced by Kaming et al. And I don't know what was the name of the paper, sorry, but I think I had it here, but I don't have it. But
Residual learning for image.
which one is that?
Deep residual learning for image.
Okay, yeah, deep residual learning for image. I thought it was written here, but anyway. So the idea basically here was that these convolutional models, they have certain problems. That one of the problems is that the more layers that you are adding, right? Technically, you're supposed to learn more, but the downstream performance goes down. The model performance starts going down, right? And then the other one was that you have gradient instability. The more layers that you have, your gradient, you have a problem with vanishing gradients, right? So it's like your gradient becomes unstable, right? And there's another one called shattered gradients. And shattered gradient is this scenario. It's like that. If you have a shallow network, the gradient behavior with respect to the data is kind of like predictive. It should be. So if your data input increases, the gradient also kind of like goes up, But in shattered, the concept of shattered gradient is that as you go to more deeper layers, this gradient fluctuates like randomly, right? So it doesn't basically follow any patterns anymore, right? So that's called shattered gradient. So all of this, we could basically kind of to a great extent basically eliminate by doing something called residual connection or skip connection. And the idea in residual connection is that you basically, if you have a model fx that as an input gets x and returns, for example, a value, residual connection says that you at the end you say plus x. You always add back the input to the output of the model. Okay. And why do we do that? Because as you go through the model, right? So your model, as the layers increases, kind of forgets what was the data, what was the original data, because the data gets lost, right? So every time you giving back the model to the layer, say, hey, carry this with you. It's kind of like take this data. So because this also is a constant, you keep doing it. So the model through the learning understand that this plus x is the data that I'm carrying it. Whatever I'm adding to this data is what was the learning at that certain layer. So the model basically supposed to learn that, right? So that idea was behind the residual connection or skip connection. Again, this is simply what you do. If you have 4 functions and this was the original function, this is what you do. You pick the output of each plus the input to that layer. So H2 as an input got H1, but you add H1 to the output basically. So on each layer, you just add the data back to it. And that helps with a series of problems. And this is how it looks. These both are the same. The first one on top, if you unwrap it, becomes the one on the bottom. So as you can see, X is the input to F1, but after the output of the F1, you add X to it. So this basically becomes this. So if this is the F1, you add F1, basically you add X to F1. Then if you go to F2, basically it becomes the output of F2 plus F1. You go to F3, becomes F1 plus 2, F2, F3. And you go to F4, summation of all four, basically. You technically, it's like if you basically unveil it, it's kind of like a look like that. It's like how you do all the summation.
What dimension?
Dimension remains constant here. You're just adding. It's like a.
Because the output of first one, like F1, might not match the dimension of the X.
Oh, I see what you are saying. So here we keep the dimensionality basically the same. You need to preserve those. Like think about it in transformer when we have all this residual connection, the data has certain embedding. So you need to basically give that. So at this point, X goes here. After this, in the next layer, that dimension could change as you go. But at first, you keep it the same. For summation part, you need to have the dimensions to be the same.
So convolution concept cannot be applied in this kind of residual neural nets, like that concept.
No, actually, the residual connection was introduced for convolutional models. So the paper that comes out is actually for image classification. So you basically add the residual connections to, I don't have any image from the paper. You add the residual connection to the convolution. So you do convolution and then you basically add the residual to it. At certain layers. So you go layer, and you do some connection, basically.
But the depth is different than the, what do you call it, input and output is different, right? Based on the kernels we have.
So no, so you don't do image directly plus. So let's say you do, for example, a kernel over some values, and then you do the values process, not the image itself, like values.
After the edition, we do the depth thing.
Yeah. We're going to, I think, we have something on the other slides. I can show it to you. Not in this one, but let's finish this one. So if you go, like what's the benefit of residual connections? Easier gradient flow because, you always, like the gradient doesn't vanish, for example. So that's scenario. It has identity mapping. What's identity mapping means that because you are doing like f of x plus x, if this one has a gradient of really small, you have a 1 always as a gradient, right? So it's like identity mapping. So you basically get rid of that problems that we have with gradient, with learning, and you get more stabilities. Okay, so let's. Oh no, this one is for you to watch yourself. I highly recommend you to, this is not Transformer, that should be CNN. I highly recommend you to watch that video later, really interesting video. Okay, so over here. Let's see. Right. Actually, let's take a break, take a quick break, and then we continue. So let's make it short because we have two chapters, two booklets to go over. Let's just make it a short one. So the idea here is that you are given some data set, some sample data that you have. These images here, these images are assumptions that is sample data basically comes from some distribution P of data, and normally P of data is unknown. Most of the time it's like you don't have it actually. You have sample from the data, but you don't have a real distribution P of data. And our goal is that to somehow trying to learn P of data, but using some some models, model families, right? So we don't have P of data technically, but we want to learn P theta. Okay, that P theta is what we want to learn here. And the distance between those two is just basically is like how good that learning was, that the distance basically. We're going to talk about. So we're going to break this down into 3 learnings. First is going to be representation. How are we going to represent the data, right? That concept of representation. The second one, which comes around is data or model families, because when you want to learn your data as a generative model, when we want to build this generative model, it's not like there's only one, there are like a series of model families that you can learn from, select from, right? So you could basically select a model from here, and that model has some parameters, and the distribution you learn over those parameters, basically we call it P of theta. Right? So you have one P of theta or representation, then we have learning, which is like or not learning, they're like a model families, and then we have this distance between, which becomes the learning. Okay, so the one thing that we will see that, so P of data is kind of like a constant, like you sample from the data, you don't have a control over, like it's the data sample that you have. We have control over these 2 pieces. The model that we select, the P of theta, the model family, and this distance between, okay? So, and you will see that as we go through the class, that all this basically different generative models that we see, the difference that they have is what they select for D, what they select for P of theta, right? So as you basically select different probability, like a model family, for finding the P of theta, you end up with a different generative model. You could pick a certain generative model, like using the same probability, like a model family, change the distance function, end up with a different generative model. Right? So if you can basically call this 1, 2, 3, right? 2 and 3 you have control over, and as you change it, you end up with a different generative models every time. That becomes the flavor of this class. As we go through this class, through upcoming sessions, we keep working with these 2, and we will see that there are different generative models from go from transformer models to go to diffusion models. They're all basically, it's kind of like we are tweaking those 2 basically. Okay, so now the overall goal that we have as we go again through the class is that we want to learn the distribution of P of X over the image. Okay, and this is basically this. It's not a P of data. It's like a distribution over the P of X. The image that you have from your model. Somehow you want to learn this somehow that you can use it for 3 tasks, for example. One of these first. Generation. Generation, that means that if I learn this P of X really good, if I sample from this model that I have, the image that I get, it should look like a dog. Okay, so that becomes the idea of generation. So I want to learn this P of theta so good, if I sample from it, it looks like a data or dog that comes from the P of theta. The second scenario is called density estimation. Density estimation comes from the idea like that if I have learned this P of theta really good, if you pass a data that comes from the sample data that comes from the P of data to the model should give a high probability to it because it should be, this is high likely to produce this image. That means that if you have this really good, learn this really good, if I pass this image of this dog, the probability, like the density value should be high. If it's low, that means your model hasn't learned that distribution. So that becomes the idea here. Now, what we will see here later is that density estimation, technically, it's kind of like a compression technique, right? That means that if I learn to compress the data really good, it's basically, it will be the same as learning to the distribution of the data. There's the density estimation. We're going to talk about that how. And the third one is going to be unsupervised learning. And the idea here is that you want to learn certain features from the data, and if you have learned, if your model has learned the data really good, this P of theta is really close to P of data, right? That means your model also should has learned the features. That means your model should know what is, a dimension for the tail of the dog, a dimension for the color of the dog, and stuff like that. So there are basically 3 problems that here we can basically address: generation, That means whatever model we learn, we hope that model be able to generate realistic data. Density estimation, the model that we learn, if we pass an actual sample data to it, it should give a high density to it, like it's like a highly possible to generate that. And the third scenario becomes the unsupervised learning, which we use it for feature extraction. Is that clear, everyone? I want you to see that if you understand this three, this what we are talking about, because it's going to be what we are going to go over moving forward.
Can you explain the second one again? Like I don't feel.
So, yes. So the density estimation basically says that think about a scenario of you doing a just unrelated. You're doing a regression, right? And you have this data set of samples, right? And basically, we wanted to do learning, right? And we do maximum likelihood learning, correct? So what's the goal of the maximum likelihood learning is that you want to find your theta that maximizes the likelihood of this data set, correct? So if you learned your theta, or if basically you learned, like you model really good, that's how you can maximize this. If you didn't learn basically your parameters, or you haven't learned really good, then that you cannot maximize that likelihood. So here the idea here is that in density estimation, if we have learned this model really, or we have trained this model and it has learned enough, if you pass an image of a dog to this model, it should give a high probability for it. If the data doesn't look like a dog and basically like haven't seen it before, also the model gives a different probability, right? But if you pick a dog and pass to the model and your model gives a low probability, it's like a realistic dog, real image of a dog, the model should, density from the probability perspective, the model should that, yeah, this is likely, this is likely to come from the density basically, right? So again, three things that we do: generation, density estimation, and unsupervised learning. Yes.
Representation learning, Professor. First two are kind of intuitive. If you can sample the data from the distribution we have learned. What about the third one? Like, how is it able to learn the features that we haven't even specified it to have the dimension?
Think about what we just talked about in convolution. You didn't specify for the filters to what to find. Through learning, the filters, through learning, basically learned what was the edge, what was the color, what was, look like a fair in the, in the tail or something, right? So that's the whole idea. If you have learned a good model, your model should also have learned certain, basically, characteristic of the image, like.
Okay, so by name, can we call to our model that give me the, representation of certain feature in an image? Can we do that?
So yes and no, in practice, it's not like that. It's not that straightforward to get the representation for a certain dimension, but to great extent, yes. Think about just a simple example like an embedding. When we learn embedding, and again, if you think about the dimension that you're learning, so you have king, queen, and man and woman, right? So let's say king, queen, man, and woman. And you basically have learned some embedding representation for all of these. So look, this could be, let's say 128 vector for each of these, correct? And if the reason in embedding, we say that if you add to, you add or subtract, basically it gives you a different value, is that certain basically axes, if you go from here to here in this direction, in the high dimensional embedding that you have, this direction that goes from man to king, woman to queen, this actually technically not necessary, but most likely carries like a royalty. It has learned the dimension of a royalty is this way. So if you search for princess, you should find it also in the same basically direction. If you go from here to here, this dimension is gender. So the reason, when we say that in embedding, if you have a higher dimension, you technically learn more, is because you let the model to play around with the learnings, the dimension, and see that, okay, what is more important in that direction, and basically you can use that, right? So here is idea will be the same, if you model basically had enough basically flexibility, and it has learned, it should understand the dimension of it. What's the tail, or what's the color, but not that will be that easy that you pick a certain layer and says that give me the tail. It's not going to be that straightforward.
So it's more likely that we hope to achieve that.
Yes. Yes. Now the question here is that how we represent the P of X. Let's look at the simple example like Bernoulli. If you have a coin, for example, you just basically we define this that comes from Bernoulli. So you have two probabilities, head or tail. This like a categorical distribution. You have K categories or something like that. So you basically have ways to present the data. Now, if you think about an image that has an RGB, and each basically channel technically has 255, right? If you think of each basically like you have RGB, it goes from 255, 255, 255, right? So if you see this cube, how many total parameters I need in order to learn this joint distribution of this image, right? So you need 255 by 255 by 256 by 256 by 256 minus 1, right? Think about it, you have a 3D, and each pixel could have basically, if you think about it, if this one can be anything like from R side, could be 255, from 0 to 255, from blue side, this could be 0 to 255, from green side, 0 to 255, right? So for each, like you have all this combination of values that could come here, right? So total, this joint probability distribution, you end up with this many parameters. Why minus 1? Because if you have out of 3, if you have 2 of them for the last one, you don't need the third one, right? So it becomes minus 1. So for an image, in order to do the learning, if you want to present the joint probability distribution of the RGB image, you actually need that many parameters. Like it's kind of like a hard, expensive, right? Now, think about a binary image. What if you have a binary image that's like black and white? It's like 2 scenarios. And assume here that the black is 0 and white is 1. Now, how many possible states for creating one image? So let's say these images are like n pixels are in this image. Each pixel is binary. If you have n pixel, total number of states is going to be 2 to the power of n. Right? So you have basically 2 to the power of n states. If you want to sample basically from this image, how many basically, if you think about it, if I sample, for example, from a pixel, it could be either 0, 1, right? So every time. So if you want to generate it, the total combination that you could generate, you need 2 to the power of n. So how many parameters we need to define this joint distribution for one image? Going to be 2 to the power of n minus 1. Again, why minus 1? Because if the last one, if I know is white or basically black, then I don't need the other one, right? So minus 1. So that's for a black and white image. Now, and we know that it's kind of like expensive, right? So what if we introduce like a concept of independency, and we see that the pixels are independent of each other? Then the joint distribution becomes basically multiplication of individual, basically probability. Now, how many total states we have? We still have 2 to the power of n states. Because a state is not the parameter. It's like how many ways you can frame this image? 2 to the power of ways n, you can basically frame it. But how many parameters do you need in order to describe that one, which they are independent? You only need n, right? Because think about it. You have a pixel, like an image that has n pixels. You can basically reframe it or basically create 2 to the power of n image out of this. But for every image, if they are independent of each other, every pixel, how many parameters I need? For every pixel, if it's binary, you only need 1 parameter. It's like a Bernoulli. You only need the probability of head. Tail is 1 minus head. So if you have n of those, I need n parameters total, right? So by making this assumption of independency from 2 to the power of n minus 1 parameters, we went to n parameters. And overall, this is a formula for if you have, for example, instead of binary, you had a 3k, like a k was 3, that becomes basically 3. It becomes 2 times n parameters. So if instead of binary, you had 3 values for every pixel. And they were independent, so you end up with k minus 1 becomes 2, and you have n of those becomes 2 times n, total number of parameters that you need. Now, how many parameters you need to specify the marginal distribution per pixel? You just need 1, right? So just 1 parameter per pixel. And the problem with this assumption of independency is that it's not realistic, right? And these images that you see down here generated by a model that we made the assumption that pixels are independent of each other. So it doesn't have any structure. It doesn't have any meaning. You can't see anything in that image, right? In compared to the original image, which was the MNIST data, right, handwritten. So that's what you generate if you make a independence assumption, right? So we take that one level further and we say that let's do other assumption like conditional independence. Instead of just directly independence, we go to conditional independence. Basically, we say A and B basically, A and B are conditionally independent of each other, assuming that C, based on some additional variable C. So that basically you can write it this way. And here also, I say X given Y and Z just becomes X given Z because X is independent of Y given Z technically, right? So that becomes conditional independence, which that's like it's like a more realistic technically. And then we have the chain rule. So if you have like n parameters or n state, and we see that the probability of joint, like a joint probability of this n states, and you can write it as chain rule in this following form. We also know the base rule, basically, it just basically we say that the posterior of 2 variables comes from the joint distribution divided by the marginal of 1. And the joint distribution, you can basically write it in this form, right? So those are like things that we know. Now let's go here and say that what if we, let's look at the chain rule and then basically let's apply the conditional independence. So using chain rule, if you define this joint distribution, how many parameters do we need? We say that it was 2 to the power of n minus 1. That's the same thing that we saw above. But if you do conditional independent assumption, basically, that goes to 2n minus 1. So it's exponential reduction, right? This was exponential and you went to all linear. Why? Because in conditional independence, we basically say that x1 is independent on all because there's nothing before that. And x2 only depends on x1. x3 only depends on x2, like the prior, the parent, basically, the parent node or neighbor, right? So because of doing that, that basically you end up with 2n minus 1 parameters. Yes.
But fundamentally, the only thing we need is P of x1, right? Because everything else will be calculated.
You mean from the generation perspective?
Yeah.
But
So
for the learning, you need to first have this to learn. That comes after the learning. When you're done learning, then right. So this is for the learning part. When you want to frame your problem, that that representation, how you're representing your data. Are you assuming because think about it. You have a data, I have this image, and I want to do the learning on it. But before I want to do learning, I need to have some assumption about it, how I'm representing this image. Is every pixel independent of each other? No, they're all dependent on each other. It's like conditional independence. So that's basically what we are talking here. Right? Then when you learn it, yes, you need 1 pixel to continue maybe for the generation, right? So, and this is just a example. So if you have basically something like this, and then you make this simplification assumption that this is independent of this one given the other one. So this basically becomes something like this. So basically you reduce the number of parameters. So x4 doesn't depend on x2. It's independent of x2. So that becomes conditional assumption, right? So now that's the idea behind base networks overall, and the main definition, like idea in base network, is that instead of using the joint reparameterization, we are basically using conditional parameterization. Okay, so that means that we have this assumption that probability of a node or basically a value is only dependent on the prior nodes or values. Right, so it's like the parent, basically. That's the idea. So that's the whole idea in Bayes network. The basically probability of each node only depends on certain nodes before that, not necessarily consecutive nodes. It could be like a parent nodes, right? Whatever this node is depending on. Right, we're going to have an image for that. But the Bayes network overall, this definition basically says, so remember on the image you have n pixels. The probability of those n pixels together comes from this multiplication of individual probabilities, and probability of individual value comes from some basically dependency on some other nodes, like some parent nodes. And what happens here is that this basically guarantees a legal probability distribution. Legal probability distribution means that a probability distribution that sums to 1 and is always positive. So that means legal probability distribution. You assume some ordering for the representation, basically, and then also it's basically highly efficient. This allows you to represent a high dimensional image with lower number of basically parameters. So this is an example of Bayes net. Here we basically say that these are the nodes that you have. The arrows basically indicates of the order and the dependency. Here, if you are looking at the XV, the pink basically here, it's independent of the greens given the parents, right? So that's basically the idea here. So you basically say every node only depends on the parents, what is connected to that node. You define this basically, define this structure for your network, for your data. And again, there is no dependency here given those ones. This one only depends on this one. It doesn't depend on the blue. There's like a immediate, basically, parent or nodes. Is that clear?
Yeah. So you're saying given the parents, XV doesn't need XN. But if the parents are not given, then XV is indirectly dependent on those green ones. I mean,
but that's not the assumption in.
Yeah.
Right? It's not the assumption that we have in Bayes net. So you see the assumption is that this is directly, it should be a DAG. We're going to go with, it should be a DAG and there's like directed acyclic, right? So you cannot have circles or, yeah, I see we have it here. So let's think about the Bayesian network as like you have this network. The graph has vertices and edges. You have one node per data point or per pixel, for example, and you have one conditional probability distribution, CPD, per parent connection, right? So every node has only one conditional probability value for the connection it has from the from the parent. So probability of an image, again, comes from this value, okay? And it's the complexity of this Bayes net is no longer depends on the number of data points that you have. It's actually exponential with respect to the number of parents, right? So the more parents you have, it exponentially grows the number of parameters that you need to learn, because it only depends on the parents, not the nodes itself, okay? So that's the set. So we basically present this as a DAG, because DAG, it has some order, and it has basically also there's no cycle in it, right? So we represent it that way. Yeah. So this is an example. Let's say for I don't know, maybe for an exam, it's like you basically say that the probability of grade, or the grade, sorry, the grade only depends, has the dependency on the difficulty and the intelligence. It doesn't have basically direct connection with the SAT. I don't know, this, for example, letter only depends on the grade. What's the grade that gives you the letter, and doesn't depend on difficulty or intelligence like directly. It's like a conditional independence, right? So, and what you see here in the discrete form of the Bayes network is called CPT, conditional probability tables. This is only for the discrete forms. In continuous form, we don't have this. So in discrete form, because you can calculate simply this conditional probabilities, you form these tables, and you use those tables as part of your process, basically. Okay, and that becomes again a comparison between the chain rule on top and the basically by factorization, and then by chain rule and by factorization here, assuming this relationship. So that becomes the difference between these two. One of them is just everything depends. The other one only depends based on some conditional relationship that we have. Now, so let's go here now. Let's go to naive Bayes. So you all assume that you're familiar with the naive Bayes, but just think about it from the generative perspective. It's a generative classification that the probability of y given x, probability of y given x comes from probability of x given y times the like this prior, right? So that's the idea in naive Bayes. And what the reason we call this like as a generative here is that you learn the probability of x given y. I'm going to talk about that. But if you think about it, probability of a label given those pixels, okay, what's the probability of a dog given this individual pixels? Comes from this value, right? And you can present that in this form. You have the label, and then you have the pixels. So pixels are dependent on the label. So the conditional independence here is that pixels are conditionally independent of each other given the label. That's the idea. That's why you see there is no connection between pixels. There's only connection pixels, and the parent of all pixels is the label. So that's the idea in naive Bayes, right? So it's just this part basically. Probability of x given y. Your data point given the label, for example. Now, that's it for the example of a spam classification. But let's go here. So let's look at the idea of generative versus discriminative classification. And you can basically look at this definition. In both case, probability of you are trying. So let's say we are trying to calculate the joint distribution probability of x and y, right? So see here. So let's say you are trying to calculate what's the joint distribution of x and y label and the data. And depending, so joint distribution, you can write it as this form, right? X given y times probability of y. You also could write it as y given x times probability of x. These two are identical, correct? These two are the same. So you can present the joint distribution of conditional x over y times prior of y, or condition of y given x times prior of x, either way. But how you present this, change your model from generative to discriminative. So discriminative model is going to be probability of y given x times prior of x. Generative model is probability of x given y, because you see the connections, right? So that's the main difference between generative and discriminative here. These dependencies that we are defining, and you can think about like this. Now, that's the same thing, like if you expand it, on top, probability of y and x, we show it as x given y. You see all the conditional are x given y, and that produces this, generative. So y always exists, and then there's this connection, and there are intra-connections also. Okay, and so in this scenario, x1 also, x3 depends on, x1 depends on x3, and so on. It's like you have all these connections, right? In discriminative, on the other end, you have probability of x1, and you have probability of x2 given x1, so there's a connection between these two, and x3 given x2 and x1, so there's all this connection, but also you have probability of y given all of those, right? That becomes the discriminative, right? So the challenge that we have here in both of this generative and discriminative, there are lots of conditionals. Probability of x given this, probability of x given this, probability of this, probability of y given this. These conditionals are not that easy to calculate. That's the challenge that we have. It's like this, all these conditionals are really difficult to find. And as we go through different algorithms, we will see that that's how, that all this algorithm, we try to somehow overcome this challenge because it's not that easy, tractable to calculate this, this information, okay? So for both generative versus discriminative, now the idea here will be that how could we basically simplify this? And that's what naive Bayes did. So in naive Bayes, which is this one, we will like, there are so many conditionals. It's difficult, like the definition of generative model. Naive Bayes made an assumption. There is no connection between x's. All x1, x2 through xn are independent of each other, right? So, and that's how you converted the problem from that to that. That's why we said naive. We made this naive assumption, but it's not that it's not that realistic. But you know, it also turns out actually it works fine for certain things that we are solving. The problem with naive Bayes is that if you think about the concept of like a spam classification, for example, and each x is a word, right? Certain words might always appear together. Like always like appear together. So in naive Bayes, when you assume that these are independent of each other and stuff like that, you technically double counting those probabilities. Because this certain words always repeat together. So you're always basically double counting for those words, you know? So that's something just to keep in mind about naive Bayes. So, and again, it's just the same thing. There's one thing here is that, remember, when it goes to discriminative modeling, because of all those conditional that you saw, and we didn't have, so in discriminative model, we don't have that simplification or assumption like naive Bayes. You have lots of conditionals. If we are missing a data point, like missing a pixel, you cannot make the classification because you need to have fully observed the data. If data is missing, some pixels are missing, the discriminative model here won't work basically. But in generative models, it's not the case. If you haven't fully observed the pixel, basically we will be able to generate the pixel as we go. So that's also something to keep in mind. In discriminative, you need to fully observe the state of the data, and in generative, you can basically marginalize over those data points. Now, as an example, in discriminative, for example, let's pick logistic regression. We basically make a linear dependence assumption, right? We assume that data are having the following form, this linear dependence assumption. And again, it's might be a really simple assumption. On the other end, we can do something like a linear, neural networks. So instead of making that simplistic assumption, we use some neural functions to using this function f to learn some nonlinearity, you know, and then basically like as move forward as discriminative tasks, whatever downstream tasks that we are doing. So, then this becomes the idea here. So on top here, we have the chain rule. This was the Bayes network, and this is the neural network, right? So the difference here will be that instead of we learning the conditionals, we use neural network to estimate the conditional for us. So you ask, basically you have this neural network which is responsible for finding the conditional. What's the probability of X4 given those ones? So instead of we learning those manually, basically we use neural network to do that, right? And we will see that as we go now, soon we will go there. It's kind of like an idea of autoregressive, right? You use neural network to find these conditional values for you. So, and actually the last line also here is that that's the basically universal approximation theorem. A sufficiently deep neural network should be able to estimate any function. Okay, so that's also that's the idea here. Let's keep it in mind. All right, so same thing. Now let's go for continuous. So that was for the discrete variables. So let's go to continuous variables. And now from probability function, we went to probability density function here. If you have Gaussian, that's for uniform Gaussian. This univariate Gaussian. Then if you have uniform, think this shouldn't be here. So you have this one. If you have continuous and you want to find the joint distribution, you can just formulate it using something like this, the joint distribution. You still can apply the chain rule and base rule also to the continuous. Like it's the same rules basically can apply here. I skimmed through this. I assume that you are familiar with the distributions that we see here. Then the next thing is that what if we want to combine this distribution? Like what if we have a continuous and discrete basically variables, and in BaseNet you can do both basically. You can basically combine these two. So you can, for example, combine the mixture of two Gaussians. So you have Z, which comes from some Bernoulli, like it's either on and off, and then you have these two Gaussians depending on the Z. Actually, it becomes the mixture of those two Gaussians. So these are the parameters you learn. Another example is that Z could come from a uniform, which also it has a continuous range. And in that case, X will come from a Gaussian with the following parameters. So something like this is like we will see later, it's called like variational autoencoder, So variational autoencoder has similar structure. And the idea over there is that you have, we will have a class on this later, but you have this network that does something like this, condense the data into some layer, and then here it gives you a mu, and it gives you like a standard deviation. You sample from mu and standard deviation, and you regenerate the image again, or the data, okay? That's the variational autoencoder. And the idea here is that that layer in between the latent layer, it comes from this Gaussian with mean 0 and standard deviation of 1. You find that Z, and you pass that Z to basically this model. So whatever is Z goes here, and Z goes here, and the output gives you a mu, or gives you variance. Right, so that's this part, the mu theta Z, e to the power of exponential of theta Z, right? So it's like you first find Z, you pass it to a function, and gives you a mu, and gives you a variance or standard deviation. The reason we have exponential here is that because a standard deviation or the variance here could be negative, so we do exponential so to always positive. That's why we have this exponential here. So, and we learn those via neural network basically. So this, we will see again this model later chapters. That's called variational autoencoder. All right, any question on that? So this was just overall quick recap, just going over the concept of representation, how we represent basically the data that we have. Just you either have full joint distribution, or you basically make an assumption like independence assumption, or you go say the conditional independence. You can use something like a BaseNet, to represent like as a relationship between node and the parent's node, and so on. Is that clear? Yeah.
So, sorry. In the case of discrete base networks, we can intuitively understand on the image and pixel values. So could you give a similar example for continuous thing in terms of base network?
Yeah. You could have a node here, for example. I don't know the temperature, right? And then you have this node that going to class, right? If temperature is, depending on what's the temperature, you either go to class, you don't go to class, right? So that's why I said this base network is not only for discrete, it can be discrete and continuous combined also. It could be continuous. If it's discrete, it's easier because you create these tables of probabilities. If it's continuous, then you need to work with like something like a probability density functions to get the probabilities instead of having a table for it.
For continuous, don't you think it is easy for continuous because we have a function, we can at least model a function, and we can just have
how do you find those mu and like variances? You need to learn those as you like. For discrete, it might be easier because you look at the data, it's fixed. Like you just calculate all those probabilities as you go. But for continuous, you need to estimate those mu and variances, right? So it's just like not that it's more difficult, but it's something that you don't have it directly, right?
Okay.
So, so here. Files. One second. Did not that file, or I have sent actually. One of these files should be the same thing. Did to myself. While I'm searching for this, any questions? So now we're going to start with autoregressive. So what we talked about right now was about representation. How you represent that, your data. Remember, there was two other parts. Was like the model families, and there was that distance, right? So we're going to now go to number 2, which is the model families. Okay. You can select the different model families for trying to learn your data, and each model family basically has different pros and cons. Different challenges. And again, this, in case you forgot the model families, this is what I mean by model families. That area, those are all possible model families that you can select from. And we're going to start with autoregressive first, okay? So, all right, so now suppose that you have this basically MNIST handwritten images, and they are like a 28 by 28. They have 784 pixels. They are binary. So technically you have 2 to the power of 784 parameters if you are interested to basically learn this probability distribution, right? So in order to parameterize this, you need 2 to the power of 784 parameters, right? And if you think about it, that's more than the number of atoms in the universe, if you want to basically learn that, right? So it's like it's pretty challenging to if you want to just learn this combination of whatever is happening. Now, in order to solve something like this, we are using a technique called autoregressive. And autoregressive, the way that it basically, and again, autoregressive is ChatGPT is an autoregressive model, right? So anything that's regress or slowly, gradually, basically predicts next image, next pixel, next token, and stuff like that is an autoregressive model. So autoregressive model, we first pick an ordering for how we want to scan the image, because you need to start from a corner and keep regressing, right? So you first pick an ordering. The thing is that about images, they don't have a clear basically ordering. Like we don't know what's actually the ordering of an image pixels. Like it's just so you can pick different way of ordering. One of the common ones is called raster scanning, which is you go to the right, go down, right down, right down. It's like a raster scanning all the way from the start to the end. So, and basically using a chain rule, we write the joint distribution for this 784 pixels as probably the first one, the second one, given first one, and so on, right? So that's the chain rule that we have for showing the joint distribution. Now, the idea here is that we can make this basically, in order, we basically can learn this via a certain type of models. And the main idea here was that let's use logistic regressions. Okay, so because we are doing a binary classification, right? So it's like is either black or white pixel. So what we do here is that after the first pixel, because first pixel we don't need a logistic regression, it just simply could come from this table. First pixel, you know, it just could, because I need the first pixel in order to continue to the rest. Could come from a random number, could come from a CPT table, a conditional probability table. But anything after the first pixel, we are using a logistic regression on it. So for predicting the second pixel, you basically want to calculate that probability as probability of x2 given x1, given some parameters, like alpha parameters for the logistic, and that logistic gives you that probability, right, between 0 and 1. Probability of third one, and so on. So probability of last pixel is a logistic regression over, or sigmoid basically over this x1 given this. And we are no longer going to memorize this or basically have a table for this conditional probabilities. We are going to learn them via like a logistic classification function or like a sigmoid function. So the idea in autoregressive is that if we have like from the first pixel, all I need is one thing, that what's the probability of being on or off, right? The other one becomes 1 minus. So for the first pixel, I only need one value. And then you go for any other pixel, this becomes a logistic regression, right? And the thing that you need to notice that is the parameters that you see, basically says that for pixel 2, we are seeing that this is depending on x1 and alpha 2. So this is equal alpha 2, or we put 2 over the up, we got 2 bottom. Okay, alpha 2, 0. So this is bias, okay, plus alpha 2, 1, x1. Okay, so that's basically what we see for the x2, and you pass that to a sigmoid function. Okay, but what you want to notice here is that these superscripts that you see 2, that tells you that alpha here is, just think about it, make it easier, W. That's alpha. Alpha is just a weight that you are learning. So W2, that means this W that you learn for bias and for weight, it's only for x2. So if we go to calculate the probability of x3, given x2, x1, alpha 2, that basically becomes sigmoid over W30 plus W31 x1 plus W32 x2. Okay. So what basically it means here is that for predicting every pixel, you have a separate logistic regression, different weights, right? So that's basically what happens in the autoregressive here, and this basically led to the earliest, one of the earliest basically generative models is called fully visible sigmoid belief network. Okay, so it's like one of the earliest like a generative model. The idea was that we make this generation using a sigmoid basically function, and this is basically how it looks. So if you want to make x1 prediction, it doesn't depend on anything. If you want to make x2 prediction, it only depends on x1. x3 depends on x1 and x2, and so on. And every line has its own weights basically on it. And there's a bias term also that later being added. Is that clear? All right. So now, if you want to do evaluation, like evaluation means that what is the probability of x1 being 0, x2 is 1, and so on. That simply becomes multiplication of individual probabilities. And probability x1 being 0 means 1 minus probability of x1, because we have the probability of x1 equal to 1. Probability of x2 being 1 is this, x3 being 1 is this, x4 being 0 becomes 1 minus whatever the sigmoid predicted for x4. Because we always predict probability of class 1, right? So And how you start the generation, you basically sample randomly for first pixel and continue generating with that one pixel. So you just need one pixel basically, and just you keep passing one pixel generated for the second pixel, pass that to the third pixel, and so on. You keep generating those pixels. Now, also, how many parameters do we need? Overall, this is N2 by 2. That's approximation. Actually, it's technically N times, N times N plus 1 by 2. That's the total number of parameters that you need. You also have an N for the basically biases, it's just that. So the total parameters that we need is that much. This is the data generated by this fully believe like a sigmoid networks. It's, as you can see, it's kind of like a model is always like a producing same thing, over and over again. So it's kind of like technically model hasn't learned much. It's kind of like a ideal, like some sort of like a mode collapses, it's always predicting some shadow area, right? So again, this was a really early type of generative model. Now, the question was that how could we make this better? So the idea was that let's use neural network as part of the process. And that basically introduced NADE, neural, basically autoregressive density estimation models. Okay, and the idea of NADE was that we picked the fully believe sigmoid networks, and we add a layer of neural network in between. Okay, that basically the idea of NADE here is that if you think about it, we have this image here. That's basically the difference. So you still have at first the connections, but what you do here is that, so in the fully believed sigmoid network, we didn't have H. We just had this connected to the output using logistic regression. In NADE, we have some intermediate layers using neural networks. So if data first goes to a neural network, it will produce these hidden layers. Then hidden layers goes to the sigmoid for classification, right? So this becomes, that's the idea of neural autoregressive density estimation technique, okay? So I will talk about data about what's this blue connections as we go forward. But so you start with, for H, you have this like a still a sigmoid here, but the sigmoid is not that necessary, but that's just for adding nonlinearity here. But you basically have this neural network makes this prediction, so give you H. H is a vector, is not a value, and you pass H to the logistic regression that you have at the end, and that gives you a prediction. Okay, so you just add a layer like a neural network in between. Okay? Now, what will happen here, so this is like a breakdown of that NADE. So if we are trying to predict H2, okay, and we say that and H2 is, remember, is the intermediate layer that we learned with the neural network. So there is a matrix, there's a vector called A1 here, and there is an X1, and there is a C, okay? So I want you to understand the dimensions here, because we want to connect this to those blue lines that you saw in the image. So what basically we are saying is that A, dimension of A, basically A1, is going to be D by 1, okay? And X is your input. It has a dimension of 1 by 1, right? So X1 is 1 by 1. And remember, X1 is either 0 or 1, on or off, right? It's like a black and white. And then you have C, so if 1 by 1 times D by 1 becomes D by 1, if you want to add a bias, bias should be also D by 1, right? So the output of this is basically a D by 1 vector. When you apply a sigmoid to it, it technically becomes sigmoid over individual element, right? So it's still D by 1. Then you pass this to a logistic regression. Now the scenario will be that if X1, first pixel, is 0, that means it was off, black, then this multiplication becomes 0 plus C. So the activation, the hidden latent becomes just C vector. If x1 was 1, becomes this times that plus that, A plus C. That's for predicting H2, right? Now, if you want to calculate like H3, the idea here is that we need a bigger matrix A. So this matrix A, or A2 here, is going to have 2 values. So it's going to be D by 2. Okay, why? Because you're multiplying it by x1 and x2. And this x1 and x2 is technically 2 by 1. So D by 2 by 2 by 1 is become D by 1. You have plus a vector C, or like a bias term, is also going to be D by 1. So again, D by 1. Right? So all H that it being produced, they're all the same dimension, D by 1. Doesn't matter how many, which position you're at. Is that clear? D is the dimension of the vector. Okay, it's like a dimension you select here.
Dimensional.
Let's say your image, let's say, has n pixels. Every pixel when you go through this neural network, you want to have a latent dimension of D. You decide D. You know, it's like the hyperparameter. Like you want to learn this latent representation of length D. So that's the dimension that you're selecting here. So now the problem here is that let's look at the number of parameters that we end up learning. How many parameters did we need for how many parameters we need for H1? H1 itself, we don't have it here, but technically only has C. H1 only has C, so D by 1. How many parameters we need for H2? We need D by 1 plus D by 1. For H3, D by 2, and then we have D by 1, right? And so on. So you actually end up with having lots of parameters. Why we have lots of parameters is because we are learning everything independently. For every H1, we are learning a totally new set of parameters, right? Like all those weights are different. And also, we at the end, after we learn all the H, if we have n pixels, you need to still have n logistic regressions. And every logistic regression has its own parameters. So from the parameter perspective, for logistic regression, you have, for every pixel, you have D parameters for weights, and basically you have D parameters for biases here. If you have n of those, you basically end up with n of this one times n, plus all the parameters that you are learning here, right? So becomes expensive, right? Now, the idea was that how could we improve this NADE, or neural, basically autoregressive density model, this estimation model was that the idea was that let's tie the weights. And that's what, you know, I think we talked about in the convolutional previous class in regularization, we talked about tying weights, right? So now the idea of tie weights is that we don't need to learn individual A for every H. Instead of learning individual A, what we do, we are going to define a matrix W, and this W has like D by N. If you have N pixels that you want to predict, you have D dimensions for each pixel and what you have. So this is fixed across every pixel that you want to use. If I'm trying to predict the value for pixel number 2, H2, I look at this matrix W, I only pick pixels that index is less than 2, or basically only the first column of this. If I want to predict for pixel number 3, I pick the first two columns of this. So W is going to be fixed across all pixels. Depending on what you are predicting, you pick the W's before that index. So if you're predicting for pixel position N, the last one, you will use all basically N minus 1 W's, for example, right? So that was the idea of tying weights. So if you tie weights, so you end up only learning D by N matrix, not N of this basically, right? So you just learn one W, and you have one like a bias also that you learn, and then you still will learn that for the logistic regression, you still need to learn separate logistic regression per pixel that you want to make a classification. So you still have for the logistic regression N times W plus N times B, but plus this D by N. So it's much cheaper in compared to the previous version without tying weights. Now, so the idea basically here will be that in if you have a model like NADE, you basically start with a random pixel. You pass that pixel and basically goes through the model, get that hidden representation, predicts the next pixel. You pick the two, pass it back to the model, and so on, like a generative stuff. Generate one pixel, pass it to the model, continue with the loop, and so on. Now, this is the example of the NADE now. So look at the in comparison to fully visible, like a belief network. This makes sense right now. Like you can read the hand digits. So on the right, what you see is the probability function, like probability values, output of the sigmoid. So sigmoid gives you a probability value, right, between 0 and 1. If you visualize them the same way between 0 and 1, without converting them to black and white, like without binarizing them, it becomes this. So it's softer. But if you pick the same thing, and for every pixel, if it's above 0.5, you say it's 1, below 0.5, you say is 0, converts to this. That becomes hard labels. Soft labels, hard labels. Right? So it makes sense. You know, this is much smoother, looks cleaner because you didn't draw the threshold. You let the model basically just give you the output and you visualize the output. Here we draw the threshold, so it's kind of like dropped some of the basic performances. So again, this will be the whole idea for NADE. Start with one pixel, find the probability value, convert the probability value to a hard value, like a hard sample, pass the hard sample to the model, predict the next soft value, convert the soft value to the hard value, and continue. So that's called neural autoregressive density estimation model. It's autoregressive because, again, it's just it does it sequentially, but also it's like a density estimation because it's capable of learning that, you know, the density value. So if you pass the data to it, it can actually tell you that what's the probability. If it has in data, it gives you a high probability value also. Now, so what if what we are predicting is not binary? Like what if it's not just black and white, but it's like a multi-class classification, right? So the idea is still the same. Just the last part is going to change is that, so here in this, what you see in the formula, let's say you have K classes that you want to select from, and on top, the H is still the same thing, the same formula. Because in latent layers, you don't care about the K class, you don't need a multi-class, it's just a sigmoid function, for example, or some nonlinearity. So you still make this H, which is a vector of size D. Then this order should be different. So after H comes the third line. So you pass H to a softmax. So if you think about it, so you have this vector. Yeah, we have this vector H, and let's say we have we basically what we want to do is that we have K classes, right? We're doing a multi-class classification technically. Like, or you're predicting multi-categories for or multi-pixel colors. And you have this H, and H has a dimension, let's say D by 1. But what you want to predict, you want it to have a dimension of K by 1. So we pass this to this linear transformation, multiplying it by some parameters over there, and convert this to a K by 1. So that's basically what happens here. You multiply H by some X, and plus B, some biases. So that basically reduces the dimension to K by 1. You pass it to a softmax. So if you have a K by 1 and pass it to softmax, each becomes a probability value, right? So now you have a vector of probability values. You can pass that to the categorical distribution and basically sample from. Right? So that becomes the idea if you have multi-class basically. So it basically, the only thing we add is that multi-class sampling at the end. Now, What if we want to use this for continuous distribution? And that is where it comes the real value neural autoregressive density estimator, or RNADE. Okay, so that's the name of this model. And the idea here is that we're no longer doing a categorical density estimation. We do actually continuous density estimation. So same idea, H, X, like everything is the same. You first find H, same thing. You pass H to a function. That function supposed to give you two things. So we are doing a basically mixture of Gaussians. So let's say you have something like this. And you know that this is a mixture of Gaussian of K Gaussians. So you know there are K Gaussians here, basically, K univariate Gaussian, you know? So what basically we say is that whatever is the H vector that we have, we want to pass that to a function, and we want that function to give us K means and K standard deviation. So whatever function we are passing H2, it's supposed to give us mean for all K Gaussians and the standard deviation for those K Gaussians. After we have that, we sample from basically, we can find the density, we can find the density value using the mixture of Gaussian, right? If you find this, you can use the mixture of Gaussian and find what's the probability density for that, or probability value for that. Does that make sense? So it's all basically, they are the same, what they do the same thing, these autoregressives. The fully belief network started with just simply a logistic function. And we saw that it doesn't learn much. It was a good try, but it doesn't learn much. So we said, let's add more nonlinearity to it. So we added a linear, basically a neural network in between, right? We created these hidden representations with some nonlinearity sigmoid, and then we put the logistic regression on top of that, if it was discrete binary. Then we said, if it's not binary discrete, so okay, remove the logistic, make it softmax, right? What if it's continuous? Remove the softmax, put a function that gives you, instead of discrete value, gives you mean and standard deviations. And if you have mean and standard deviation, then you can basically pass it to the mixture of Gaussians. Yes?
Can we go with a simple example? Like, just we give height and weight and generate people.
We give height and weight, and we generate people. Okay. Now, if you are taking think about it like an image, for example, right? So you give a pixel, right, and then you generate next pixel, right? So from the perspective of that's an image. Like I'm trying to tell you that they don't give height and weight to generate human. If you want to generate words, you give a current word and you generate next word. And you have the last two words and you generate the next word, right? So it's kind of like that's how you make the prediction, right? So the continuous could be image in like colors, right? But you don't give height and weight to generate
because of that sequential.
Yeah, yeah. So we are not using it to generate humans' images. Right? Actually, this
I wanted to like use a simple example for continuous variable to get the hang of this edge.
So the image like a colored image. We were looking at the binary images.
Can we go with a 3 pixel by 3, 2 pixel by 2 pixel image? But I don't know. It's a little bit difficult. I don't know.
2 by. You mean what type of example are you asking me for?
Like, okay, so
let me see if I get what you mean.
I'm having a hard time to figure out the role of H here. Like what's happening?
H is just a hidden vector. I think I get what you mean. So let's say let's break this down. So we want to, given this pixel, doesn't matter, it's discrete or continuous, right? We wanted to predict next pixel. First time we were like, let's do direct shot, and we do a sigmoid, right? Whatever is the value of this pixel goes through a simple sigmoid, like a logistic regression, right? So weight bias plus weight times whatever is the x1, right? And we said that we saw that it doesn't actually produce anything. Why? Because it's kind of like a really naive assumption. You can think about it like that. Too simple, right? So the idea was that, okay, what if instead of directly doing that, we have another model that is responsible for learning some hidden representation. Exactly. So we are going to put another model in between. That model is responsible for learning some hidden representation, H. Okay. The dimension of this H is the, but you can decide how, think about when we were talking about embedding, the more dimension you have, the more learning you have. You can also think about like that, what you want to decide this dimension to be. Whatever is this dimension, too large, too small, at the end, you need to, with the second function, so there's a one function to give you H, second function, you need to reduce it again. Because you want to bring it back to a prediction of the pixel, right? So that's the idea of this inner H. It just, we want to learn some representation which just by a sigmoid wasn't possible. So we bring another model and say that, hey, you learn this hidden, like a representation of hidden features that I could use to predict the next pixel. Right? So you add additional layers to it, additional, complexity to it. So, answer?
Yeah, that's better now.
All right. All right. Sorry if it wasn't clear before. So, and again here also remember whatever we learn for a standard deviation, or we need to ensure that it's apply exponential to it because otherwise it could be negative. Okay, so you always apply that exponential. Now, we're going to compare this to an basically autoencoder, because if you think about it, it's kind of like it has similar flavors. You just have a data, you basically taking it to some hidden representation and then bring it back to the data. Right? It's kind of similar, look like an autoencoder. An autoencoder is what you have on the right. You have a data, you do some processing, it either expand it or decrease the size, but then you regenerate the data from. So data goes in, data should come back. Right? So basically you model it to learn to break down the data, and then reconstruct the data. That's the idea. Now, and this is basically what happens internally in an autoencoder. And it's like it has all these weights that processes the data goes. So it has the first part, it's called encoder. The last part called a decoder, basically. The decoder gets the H from the encoder. Using that H, basically represents the, regenerates the data. And again, we will have autoencoders later coming, but if you think about from autoencoder perspective, encoder, decoder. Encoder job is that to encode the data, and the decoder job is that to get the encode and reproduce the data. So these two, if you think about from the perspective, they kind of need to, both they need to get improve by time. Encoder should get really good at getting a data and extracting meaningful information out of it somehow, that the decoder also can be, should be really good, that gets that like a dense representation, like a hidden representation, and be able just by using that regenerates the data. So these two basically work like in sequence together, right? So, but the difference here is that if you think about an autoencoder, it's not like a vanilla autoencoder. It's not generative. It cannot generate anything for you. Okay, so the cost function for autoencoder, if you do binary, it's going to be like a binary cross entropy. If you do continuous case, it's just simply points minus whatever you predicted for the point, right? Just a similar of like a other neural network that we have seen. And again, the problem of the vanilla autoencoder is that it's not generative model. So it cannot generate model. So the idea was that how could we expand an autoencoder so it becomes generative? And we can do that by enforcing like some sort of like ordering, some sort of like a similar to the BaseNet that we have some ordering. So we can basically introduce some ordering here by masking basically, and that's called mask auto encoder mask auto encoder. It's basically the whole idea is to think about you have this fully connected autoencoder, and your goal is that similar to BaseNet to say that certain nodes only can see data from other nodes. So in order to do that, you force the weights, the connection, to go to 0 between the one that they are not supposed to see each other. And that basically enforces this relationship. Now, if you have something like this, it actually generative, so it can generate generates data basically for you, right? So because again, we have this like an ordering that basically like a parents, like similar again to BaseNet, like we have this ordering of nodes and the parents, and we also basically enforce that certain points maybe they don't, like for example here if you look at x2, px2, in order to predict that there is no connection actually. It doesn't depend on anything. You basically could randomly generate that point. You know, it doesn't depend on any preceding nodes. All right. So the importance here is that for mask autoencoder is that you basically need to ensure that every unit, for example, x2 doesn't depend here. Unit x2 doesn't depend on anything. x3 based on the image only depends on x2. And also you need to be sure that, you know, it's kind of like when you look at the last layer, all the, there's a restriction, you have a strictly basically followed the rules. That means there shouldn't be any connection between nodes that they are not supposed to see each other. If you can do something like that, and you get basically like a mass autoencoder, again, you can use it for generative. So, again, to summarize on autoregressive models, and again, we will talk a lot about autoregressive model moving forward. As like they are easy to sample from the autoregressive model because all you need is one starting point, and you can basically continue. One of the challenges, as you can see, is like the sequential part of the process. So it's like a take time to generate. That's why, like, if you think about GPT or generative models like that, words comes one at a time. So it's kind of like you cannot look ahead. If you want to compute probability, also you find the probability of one, the probability of second one given the first one, and so on. You can easily extend it to continuous, or basically you can be discrete. Basically, another downside is that there's no natural ways to get features out of it. Like it doesn't give you information around the features, or you cannot use it for clustering and stuff like that. You know, so that's something to keep in mind. And an alternative approach we will talk about in the next class is going to be RNN. You're using like a recurrent neural networks to basically do just generative. Those also have some flavor of autoregressive because it's going to be one token at the time you're using it for prediction. All right, so I'm going to start just for, I don't know, like 5 minutes, and then to give you some flavor of what we have for the next class, and then we stop after that. So now it comes to point bullet number 3 is that, so you have a model family, you have a presentation of the data, how you figure out that if I learned something, like the part number 3 becomes like that learning, right? So again, this is the scenario we have. And as I said that the choice of model family or the choice of basically this density, like a distance function, will change the generative models that are out there. So if you, as we go through the class, different generative models, we do the same thing technically, but either the model family has changed or the distance function has changed. Okay, so just by picking some other distance function, you end up with a different generative model. Now, and again, the goal was that we want to either do generation. That means if you pass a pixel or something, or sample from this model, it should look like a real data. If you pass a real data to the model for density estimation, it gives you high probability because it's real. And we're hoping that we can also learn some representation from those models. Now, the first question that we have here is, okay, how do we learn P of theta, how do we represent P of theta? And we went over the autoregressive example. That's one model. We select a model family, basically. And then, okay, how do we learn it then? We pick the model, and model has parameters. So how we actually learn those parameters. And scenario basically here could be like that. If you have this data set, for example, we make this assumption of IID. We say that the data points are, kind of like independent of each other, come from the same distribution. And then we basically given set of model family, we pick one model family for it, and we hoping that to learn the best model family technically. We basically say that we are hoping to learn the best model family. And these are the two examples that we just saw. You could do BaseNet, you could do fully visible belief network, you could just do, I don't know, like an RNADE, NADE, or different type of model family. But the main challenge that we will see here is how could we learn this if we only have access to sample data? And that's the problem with the generative modeling overall. We don't have the origin, we don't have the real probability of data. We don't have the real data distribution. We only have access to sample data, right? So if you have access to sample data, how could we basically learn this problem, or how could we learn that? And again, this is just an example of the same thing that we talked about. If you think about a pixel in a binary image, end up more than number of atoms in the universe. So how we want to basically learn something like that. So the other question is that when we say we want to learn the best model, what is the best model? Like what we define as best, and that again, that depends on the task that you are interested in. If you are doing a density estimation, basically best model is that you're trying to find the full distribution, or you're interested in to learn that distribution, or basically or to learn it somehow that if later I pick a data point and I pass it to this model, it can give you that, what's the probability of this data point. If I'm doing a prediction task as a downstream, my goal is that to whatever model that I learned, it basically can give me a best, I don't know, F1 score, for example. Or if you're trying to learn the knowledge discovery, maybe you want to try to see that how to genome basically interact with each other or something like that. So it's like a different downstream task can define what's best. And the main question that I'm going to stop here is that, okay, so let's say we have some idea of this probability of theta, and we have some of the idea for the data sample that we have. How could we measure that, how close are these two? How we measure this closeness, like this distance between these two. So that distance, again, as we will see, that the choice of the distance function will lead to different generative models. So that will become what we basically will discuss in the next class. All right.
So to tie together,